Welcome to Math 104, Chapter 1.2, where we talk about graphs of functions. So here we have graphs of polynomials, and each graph is paired with its own parent function. Of course, some of these functions will get more complicated as we go out throughout the semester. We've talked about lines, your slope, your y-intercept, which neither are quite showing, right? But we do know that lines get a little bit more complex. These are just called your, parent functions. So it says the degree of a polynomial is the highest power of our variable. So looking at your variable, x here, if we don't see the degree, what can it be assumed? Well, it can be assumed that we have a 1 right here. And then again, our degree here of your polynomial is a 2. Even if we were to tack on some more, some more feedback to it, right? Going in order, descended order, next would be bx to the first plus c, where all of these are just kind of supposed variables and their coefficients. And you can see here, again, just your degrees. Now, are there any sort of patterns happening between your degree and your graph? We'll take a look at the even degrees. Your even degrees, such as 2 and 4, what are their graphs doing? Well, they look pretty similar, right? If they're looking pretty similar, they're both going up, right? That behavior of your graph, they're both going in the same direction. So that just means that any sort of degree that has an even number or an even degree, so let's say x to the 6th, that should have this sort of shape where, again, their direction will be the exact same. And of course, these are all positive. We could, if we wanted to, flip it over and continue down. But even as we flip them all down, notice that the direction is going the exact same. Now let's do the same, but look at your odd degrees. So 1 and 3. Looking at their direction of the end behavior, what can we determine? Well, one of them is going up and the other one is going down. So these are alternating. One goes up, one goes down. They're going in different directions. So that just means any odd degree will end up in different directions. So that means if we did x to the 5th, we would go in a different direction. And again, these are just, these are the positive counterparts. We know that we can have a negative line if your slope is decreasing, if it's a negative. And same thing down here, we could go in the reverse. It just all depends on the coefficient, if it's negative or if it's positive. If they're all positive, they're going to be having this general shape of all trending upwards, or if they're all negative, they'll go in the opposite direction. They'll start falling. Now let's go ahead and graph. So can you guys pause this video and see if you can graph x squared plus 2 on your Desmos? So looking at it on Desmos, if we were to take it out, we have y equals x squared plus 2. So this is our graph right here. Now we have our general shape of that U shape, right? And we can determine that it is that U shape also by looking at your formula. So looking at your formula, what was the degree of your polynomial? What's the highest degree that we see, which means it's a degree of 2. It's an even degree. Your general shape, therefore, should be going up. And if that were negative, it would be going down. And again, we're never expected to just know what it is based on your formula. We're always going to be using Desmos or some sort of graphing calculator for you guys to check that. Now, when it comes to your turning points, how many turning points do you see on your graph? Well, there's only one turning point, right? It is where your graph just changes direction. We were starting to fall on the left-hand side, and then all of a sudden we stopped and then continued to rise. Now, at what point is that? Well, when you tap your graph, you'll notice that at the point 0, 2, this is where your graph decides to make a turn. It turns right around and goes in the opposite direction, kind of like it made a U-turn. So turning points, we have only one turning point. This was at the point 0, 2. Now, turning points can be either classified as a minimum or a maximum. Now, they have sometimes some special names. Sometimes they can be called a local or a relative max or min. Local and relative mean the exact same thing. It's just whether or not you took the SATs or ACTs, but they mean the same thing. You can have lots of turning points, but they're either going to be the peaks and the valleys found on your graph. So for us, when we talk about that word again, we said local or relative, maxes and mins. These are peaks and valleys found within your graph. Whereas the extremes of your graph, these can also be classified as the absolute max or min. This can be either a positive or negative infinity or a specific point. For us on our graph, do we have a minimum or a maximum? Well, our minimum, right, is the smallest point that we have, right? The smallest y counterpart. All of a sudden, we stopped your graph at the point 0, 2. Your y values, your y coordinates do not get smaller than 2. Therefore, we have a minimum. We also have this particular point as our absolute minimum. So you can notice that this can be one of two things. This can be called, if on our graph specifically, maybe I take a picture of it. Oh. There we go. I'm still kind of learning my graph here. There we go. Let me save it. Save it to photos. And if I put it on here, there it goes. So ours can be classified as both a local or relative. I like to use the word local minimum, and an absolute minimum. It all depends on the shape of your graph. Now, a turning point is a change in direction and can be found by an equation where it says the number of turns that you have is equal to n, where n is the highest degree of your polynomial, minus 1. So if the degree is 2, therefore n is equal to 2, how many turning points are there? We can say, okay, well, the number of turns is equal to n minus 1. 2 minus 1, which is equal to only 1 turn, which we can see that here, which is super apparent. Even if we had another x term here, it would have to be less than 1. So we have your degree of 2, and we said that this can only have 1 turning point. And there you go, 1 turning point. Now, what if your degree is 3? How many turning points do you have? Well, the most that you can have, again, the number of turns, is equal to n, which in our case is 3, your degree, minus 1. Means that we can have at most 2 turns. So now let's have you guys try example 1 on your own. So can you sketch the graph on Desmos first, and then perhaps you transfer here? On the function, f of x is equal to x cubed minus 3x as seen on Desmos, and then answer the following. How many turns do you have? What degree do you have? Are there any local or local maxes and mins? And can you write it as an ordered pair? What does it mean by writing it as an ordered pair? Well, this is looking for a full coordinate. So your answer should be structured as this. So now let's go ahead and put that into Desmos. So we have x cubed minus, let's see, let me take out my notes. That would be helpful. Minus 3x. So this is our graph right here. And I'm going to just shift around my graph. And now I need to determine how many turns. How many turns are we seeing? And I might even, let's see. Oops. One more time. There we go. I'm going to do this one more time. Sometimes I don't like putting the graph onto your notes just because I want you guys to see it on your own graphs instead of me giving it to you. Let me go ahead and transfer that right here. There we go. There's my graph. All right, so how many turns do we have? Well, our graph starts to climb and then all of a sudden we change directions and then we start to fall and then one more time change directions. So we have 2 turning points and your degree is your highest degree of your polynomial. So you'll notice here, we have a degree of 3 here and a degree of 1. So 3 is higher and that would make sense. We can have 1 less the amount of turns. Now your local maximum, where is the high point found on your graph? Well, this is at the point, this high point here, this peak is located at -1, 2. And notice how I'm writing my coordinate, my ordered pair as -1, 2. That's what our answer needs to be when it says write as an ordered pair. And again, your minimum is the low point, the little valley of 1, 2. Now, when it says, let's create a 10 by 10, and this should say a -10 by 10, a -10 by a +10, and again, a -10 by a +10. This is telling us the window. Well, on your homework, when you see it like this, the first one is going to be your X window, and the second one is going to be your Y window. So let's go ahead and see that on Desmos. There we go, Desmos. To get to your window, you're just going to hit the tool function. And notice that on your x-axis, right, we're going to click your smallest one, and that is going to be -10, and your +10 over here. Steps is just your scale. How much do you want to go by? They didn't tell us anything, so we're going to leave it alone. And again, a -10 for your y and a +10 for your upper y. And again, your step here is just how much do you want your x values to go up by or your y values to go up by. So this is your how to get the window that it's asking for. And you'll notice that each of your extremes on your window, so left, right, up, and down, they end on either a positive or a -10. So there we have it. Now let's have you guys try example 2. See if you can pause the video and try it on your own. So it says using your graphing calculator, graph the function and find the following. So we're going to go ahead and enter in this graph into Desmos. It says first select the standard viewing window. All that is saying is, can you just click the house button on Desmos if you use Desmos, and that way it kind of just resets everything. Then it says next put in the following window, which gives the better view. So we're going to do one of 2 views and figure out which one is better. So let's go ahead and reset this. We want, let's see, x cubed, so that one was okay. Then we have -3x squared. Notice that as we're doing this, it's manipulating her graph, which is always fun to see, -13. So right now our window isn't very good. When it says do the standard window, I'm going to click the little house button and that kind of resets everything. Now let's put in our viewing window. It says a -10 by 10. That's going to be your X window. The one that comes first is always your X. Notice that thankfully it's already been set for us. Then it says a -30 by 15. So a -30 for your Y. And again, +15. Now, what do you think? Not bad, not perfect though, but Again, let's just see your other one to compare. Your other one says a -5 by 3 and a -15 by +15. All right, what do you think? Obviously, the first one is loads better than this one because it's missing a huge chunk of your graph. So let's go ahead and snap it back to the first one. Okay, so this is our viewing window that is preferred. So now it has a list of things to ask for. And I'm going to go back here and we're going to select this one. And again, this is your X window. And this is your Y window. Now, if you are doing your graphing calculator on just your phone app and not Desmos, all you're doing is just selecting the window, and then it says X min, X max, Y min, Y max, and then your scale, your X scale and Y scale, you can just set that to 1 or whatever preferred jumps you want to go up by. And when it says B, it says find Y when X is equal to 5. So when X is equal to 5, this is what we know your X value to be. So we need to find your Y value. So in doing that with Desmos, we're going to open this part up. We're going to tap our equation and go up to that little circular gear button, kind of like the settings button. And then we're going to tap the chart. And you'll notice that it pulls up a series of values of X's and your Y counterparts. And one way we can do it is also keep on hitting enter until your X value pops up. Now, this is nice if it's kind of close to the range that we want. If it's a value like when X is 100, we might prefer to actually enter it into your formula and actually put in your X value algebraically. Or you can manipulate your graph and kind of use your finger as like a little tracer. Come on. Oh, it might not work here. There we go. As like a little tracer. Come on. Probably because I'm already in here to kind of determine what your X value is. So you can see though here 5 maps to 37. So we clicked on the equation, then settings, then click on table, and also find algebraically. Now let's try it again with C. Find your X this time when Y is equal to 2. Well, what's nice is that Y is equal to 2 is in fact an equation. So we can put this into a new equation box. So create an equation. And let's see what that comes up as. So you can get rid of that. Let's do when Y is equal to 2. Now, what do you notice just popped up on your screen? Well, we can see a very nice purple horizontal line, Y is equal to 2. And what is it doing to our graph in red? Well, it looks like it's intersecting your graph. Well, it's intersecting at a particular X value. So that Y value that we have mapped is now touching our X graph at 3.96. So that would be our X value. When X 3.96 comma 2. And you'll notice that I like putting it into a coordinate. Let's have you try it again with D. So again, you can do the exact same way that we did this before, where you set Y is equal to 0. Now, anytime Y is equal to 0, though, that was special. What did we say it was previously? Well, this we said was really your x-intercept. So we don't really need to do much other than visually see our graph. Where is x equal or y equal to 0? Well, y is equal to 0, your x-intercept is anywhere where your graph touches the x-axis. Therefore, you can see here when I touch that coordinate, we have y is equal to 0, and then your x value is 3.87. Or you could also do it as y is equal to 0, And then again, wherever it intersects, it's going to be the exact same. Okay, let's have you guys try example 3 on your own. It's very similar to the one that we've just done. So example 3, a little bit more of a real world context. It says the following experiment represents a ball being tossed into the air where height is a function of time, where it says h is equal to negative 16 x squared plus 120x plus 5. Find the height after 1 second and 5 seconds. And then when it says, what do you notice? How is this possible? I think this was from an older version where they were both equal to one another. This is no longer true. Okay, so one way we could do it is algebraically, and we can work it into your equation, and then again here and determine it that way. If we wanted to do it graphically, all we have to do is change your graph. Oops, just do another home screen. We have negative 16, or y equals negative 16 x squared plus 120x plus 5. Now you'll notice here that we now need to work on a window. So what is an appropriate window? Well, some context we can use is your constant, the plus 5 on the end. Sometimes that's a little high. Ours isn't very high, but you'll notice that her parabola is going up really quickly. Therefore, when we use our tool button, we want to change perhaps your y-axis maximum. So let's go ahead and try 50. That still doesn't do it. We're getting closer though. Notice that they are getting closer together, the red line. Let's try again, 100. And again, you'll notice that it's getting better, still not quite. We want to see the rounded edge. So let's try maybe 200, getting a lot better. And one more, 250. So here you can see a nice fluid parabola that we can see at the very top as well as on either side on the bottom. So now let's go ahead and figure out where our x is equal to 1 and x is equal to 5. So we could do this if you wanted. Oops, didn't mean to actually do that. Notice that you can put your cursor on here and determine, okay, well, at what point is it going to be equal to 1? Sometimes that's a little hard to do. Notice that I jumped right over where it came out to be 1. And notice that I can't get it to stick. In which case, what is nice is we just tap on your equation, the little gear symbol, and then the chart. And we'll notice that at 1, we are at 109. And then again, if it's not enough, we want all the way to 5. I can keep tapping and entering until it gets us to the value I want. I won't suggest this method if our x value is really, really high, in which case I would just go ahead and enter it in. Or if it's any sort of fraction, I would enter it in. So you have 109 and 205. H of 1 is equal to 109, and h of 5 is equal to 205. Now let's go ahead and find the maximum height of the ball. When does this occur? Well, the max height of the ball is how tall did it get, right? Maximum height. So your max height, if we just tap, is at 3.75, 230. And I'm going to write that down over here. Now, which is which? Well, keep in mind your x value is always time. This is your time value. In our case, it's going to be seconds. They told us it's seconds right here. And therefore, this one is your height. So the max height of the ball is 230 feet. And your seconds it takes to get there is 3 seconds and 3.75 seconds. Now, what time does the ball reach the ground? So keep in mind our parabola. What goes up must also come down. So what we're really looking for is right here, where this height is equal to 0. This is the ground. And so therefore, we're looking for your x-intercept. So for us, your x-intercept, notice that it looks like you have 2, but notice that when I tap my x-intercept here on the left-hand side, it's giving me a negative time. That is not possible. So instead, it's going to be our right counterpoint. So we have 7.54. So it will hit the ground in 7.5 seconds or so. Now, I will ask one more question, just because it comes up on your homework. When does the ball reach 100 feet? Well, 100 feet is your y counterpart. Height, or y, is equal to 100. So let's go ahead and put that equation in. Y is equal to 100. And notice that it's touching your parabola twice. Is that okay? Yes, it is okay, because what goes up must come down. This ball is reaching all sorts of different height, and the only time it hits a height one time is when it is all the way at the top. So for us, when it touches 100 feet, it's happening both at 0.90 seconds and again at 6.6 seconds. Now, if you have to pause the video here, for example 4, I would say wait for example 4, because this is the first time we're going to start to manipulate some of our x values. And then from here on out, you're going to notice that there's one magical sentence that will change all of your answers. And sometimes that is the reason why we get them wrong. So for example 4, it says, the average teacher salary is given by the function f of x is equal to 900x plus 32,000, where x is the number of years from 1992. Now that is our magical sentence. So when it says A, what input value? It's saying what x value corresponds to the year 1992. That is just saying x is equal to what when it is 1992. So we're starting this data initially in the year 1992, but we're not using 1992 for your x value. Instead, we're using your x value as if it hasn't occurred yet, meaning that your x value is going to be 0. So when we see the year 1992, we're going to enter in a 0 into your equation. Now, when it says what input value corresponds to the year 2012, not 1912, it's saying what x value now is for the year 2012. Well, keep in mind, we're starting at the year 1992. That's when we initially start, so that's 0. 1993, therefore, is what? Well, it's 1. Well, how did we get there? It's the difference between 1992 and 1993. So 1994, that would be 2. 1995, that would be 3. It is the difference between these values from the initial value. So the difference between 2012 and 1992 is 20 years. So x is 20 for the year 2012. Now, what outcome or output corresponds to the input for 1992? Well, keep in mind they said we're going to be using your input value of 0 when we want to look at the year 1992. So when x is equal to 0, keep in mind thinking 1992, we can either enter that in graphically or enter it in algebraically or see it graphically. I'm going to be doing it by hand. F of x is equal to 900 times 0 plus 32,000. Now, the reason why I'm doing it by hand is that you may have graphed it and seen it straight line, right? A straight line that is going vertically. Now, it's not going vertically. It is actually just a very, very quick slope, because notice that your slope here, it's going 900 units up for every 1 unit over. So that's why it looks a little strange. So for us, when I put in my X value of 0 for the year 1992, I get out $32,000 because again, this is context, right? We're talking about teacher salary. So could we figure out what does this answer mean? Well, in the year 1992, teachers' salary were on average $32,000. Now, can you try that again, but with D? What output values correspond to the input for 2012, and what does your answer mean? Well, 2012 we said was 20 years later. So F of 20 is equal to 900 times 20 plus 32,000. So you get 18,000 plus 32,000 is equal to 52,000. Nope, 50,000. There we go, 50,000. And again, what does this mean? In the year 2012, the teacher's salary were on average $50,000. Now, for E, it says use the above to find an appropriate window. Look how large your Y values are. We're at 32,000 at 0, and again, 50,000 at X is equal to 20. So when we go to build a window, right, they're kind of leading us into a direction. What X values did we use? Went from 0 to 20. What Y values did that correspond to? 32,000 and 50,000. So let's go ahead and see what that window looks like when we go to graph. So I'm just going to kind of just go back to a normal screen. So you have Y equals 900X plus 32 plus, there we go, 32,000. For some of us, it may not have even popped up, in which case you might were like scrolling and then it looks awful, right? Well, of course it looks awful. We got to manipulate your graph. So let's go ahead and put in our built-in window. We're looking at some sort of 20-year gap. And then for your Y-axis, we're looking at, oh, and I don't know why I put 32, right? 32 is where your X values start. Let's start your Y values at 0. There we go. And then if we want to change, let's go from 0. And then we go to 50,000. What do we think? Right? We might not want to start at 0, right? Notice that there's so much of a gap, but it's a good estimate of what this thing should look like. And again, it gets us an appropriate viewing window. And then from there, we can kind of make some estimates. It helps us find your starting place. Even if we did for your Y value, and of course, look, I messed it up already for your window, 20, 0. Maybe we did the 32,000 and the 50,000, right? Not a bad window. It looks really good. It goes right across our screen. For me, I like a little bit above and below as far as like a cushion goes, but that's not a bad one, right? Use your X values and your Y values that you've plugged in to get a window.